Okay, Assalamualaikum and a very good morning to everyone. So today we will continue our next chapter, which is chapter 2 regarding on the Fourier series in our signal and system course. Yeah. So in this course, you will learn about the signal expression, time domain signal, frequency domain spectrum, and also complex exponential. Okay, students, let's look what is Fourier series is all about. So Fourier series is used to represent the infinite sum of periodic signal. So basically, what is periodic signal? So periodic signal is a repeating signal. Okay, is a repeating signal by period of t naught. Okay, in a form of simple signal. So usually it is a sinusoidal signal. Alright, so when I said it is a repeating signal by period of t naught, so here t naught here is the fundamental period. Okay, so the first of t naught here is known as the fundamental period. Okay, so the next cycle or the next repeating signals were going to be the numbers of n. Okay, so this is 2n, 3, the 2t naught, 3t naught. Okay, and what are the advantage of a Fourier series? What are the use of a Fourier series? So Fourier series is a signal generated, commonly a non-sinusoidal signal, okay, but periodic, okay, which are difficult to analyze. To analyze. So it is a representation in sinusoidal form, which is much easier to be analyzed. So we want to make the non-sinusoidal signal to become a sinusoidal signal, which is easier for us to analyze the signal. Alright, so that is what we're going to do in a Fourier series. So what are the applications that we can learn in or we can apply this Fourier series at? So these are the example of the applications, and it can be represented into two forms. One is the trigonometric forms, and another one is the complex exponential. So the trigonometric form, also known, sometimes it is be called as a polar form. Yeah. All right. So these are the advantages of the Fourier series. Yeah, signal generated are commonly non-sinusoidal but periodic, which are difficult to analyze, and representation in sinusoidal forms are much easier to be analyzed. Right. So let's see some example. So consider this periodic signal. We have this kind of signal, right? And as the first signal, the first equation here is our fundamental period. Okay, so if you try to plot, it's gonna look as such. And for the next period, okay, so this is the next period, the following period, and so on. And if you plot, we can see it's gonna look as such, right? Okay, so any periodic signal can be represented by series of sinusoidal signal. Okay, so now let's look what is the signal spectrum. So signal spectrum is a periodic signal in time domain that can be represented by its amplitude and phase spectrum, and usually it is being seen as in frequency domain, and this is what we call as a signal spectrum that you guys will be introduced or gonna learn or go through this when in your basic lab later. Yeah, so these are the frequency domain, okay, to represent the periodic signal that need to use in a signal spectrum. Okay, and this signal spectrum can be represented in the amplitude spectrum and also the phase spectrum. Yeah, so this is another amplitude modulations, okay, which you guys will learn in lab session, okay, basic lab in year 2 later. Yeah. Okay, now let's look at the signal expression. So the sinusoidal signal is a common type of signal used in communication, and usually it is represented either in a sine or cosine. Okay, it can be considered a time varying voltage signal. So for example like this, okay, so V here is representing the voltage, okay, and inside the bracket T here is representing the time varying signal. Okay, so the A naught here is represent of the peak amplitude, and the omega naught here is known as angular frequency. Okay, and which we know the angular frequency will change by time, and plus theta naught here is the phase change. Okay, this equation also can be written as such. Okay, we can rewrite this equation to become as such, where from cosine to become sine, of course it will have a phase change. All right, and then omega naught also, it will we can represent it as a frequency, which we know omega is equals to 2 pi f. All right, so when we have a sine, we want to change into cosine. Okay, sine change to cosine, there will be a delay of negative pi over 2. Okay, now let's look into the time domain signal. Okay, so sinusoidal signal can be sketched in time domain graph, and it is considered a time varying voltage signal, for example, as such. Okay, so this is a time varying voltage signal, and this is written as sine. And if it is written by cosine, we can see there is a phase delay here, so therefore it will gonna be minus pi over 2. Okay, so if it is from cosine, you want to convert to sine, they're gonna be phase advance, yeah, plus pi over 2, right? Okay, now let's look into the frequency domain. Okay, into the frequency domain. Frequency domain spectrum. Okay, so each sinusoidal signal has a frequency. Okay, so usually frequency, the symbol is written as F. Okay, in hertz or angular frequency. Remember, F is the frequency where the unit is hertz. However, for omega, the unit is radian per second. Okay, and amplitude A, amplitude we're going to be represented as A. So here is the amplitude, and then we have phase. If there is a theta, okay, meaning that there is going to phase delay or phase change. All right. So this is the form of trigonometric function, or also known as a polar form, where a polar form, you can see it is in a single-sided. What I mean by single-sided? If you look here, the graph is only represented in one side. Okay, in one side. So later you will see when in exponential form we have a double-sided, but in in a trigonometric function we only have one-sided. So how to draw this graph? Okay. Yeah. It doesn't move. Okay. So how to draw this graph? Okay, so this is a single-sided spectrum graph. Okay, so this, the first, 2 pi f here, it is represented as 2 pi f. So this is known as omega 1, angular frequency, and this is the phase change when it is on omega 1. Okay, phase change at omega 1, and this is the amplitude. So usually in a frequency domain spectrum, since that it is known as frequency, our x-axis will gonna be in terms of omega, but sometimes it also can be represented as f, frequency. So usually in normal cases we will represent it as omega. So we have omega 1. Okay, so omega 1 represent, for this omega 1, okay, ini adalah omega 1. So omega 1, what are the amplitude? So the amplitude is A1. Okay, so this is the amplitude. So we have two graph. One is amplitude graph, another one is a phase graph. So amplitude graph, we only plot the value of the amplitude at the angular, at this specific angular. For example, omega 1, the amplitude is A1. At omega 2, so this is omega 2. Okay, this is omega 2, the amplitude is given as A2. Okay, so this is amplitude spectrum graph. Next, if you want to plot the phase spectrum graph, our x-axis is still remain to become omega, okay, angular frequency. Okay, our y-axis we're going to become the voltage value. But now, since that this is a phase spectrum, we want to plot the phase. So at omega 1, okay, let's look here. At omega 1, okay, the value of the phase is theta 1. Since that it is a positive, okay, since that it is a positive, it is pointed upward. Okay, it is pointed upward because it is positive. So the value is how much? The value is theta 1. But for omega 2, so this is our omega 2. Our omega 2, if we look here, the value of the phase is negative. So it is pointed downward. Alright? So that is how we want to determine either it is pointed upward or it is pointed downward by looking at the positive and negative. Alright? Alright, so now let's look at this example. So in this example, the question asks about to plot the amplitude and phase spectrum. So meaning that we need to plot both the amplitude and the phase spectrum for these given equations. So first of all, before we plot, we need to see and we need to observe first either this signal is in a general form or not. So first of all, we need to identify we have a negative sign here, and we have another one sign. All of this is cosine. This is also cosine. However, the last equation is given as sine, and also usually it is given as positive, but now we have a negative here. So what we need to do is we need to rewrite the equation. We need to make sure that all of the equation is uniform in a cosine form. So therefore we need to rewrite the equation, and we need to use this hint in order to rewrite the equation. So for the negative cos theta, okay, based on this hint, to make sure that it becomes a positive, we need to have a phase change here. Okay, alright, so we need to add pi, and for sine, in order to change into cosine, there's going to be a phase delay of negative pi over 2. Alright, so once we rewrite the equation, that we have make sure all of the equation is in a cosine form and everything in a positive sign. So next, we can draw the spectrum. Okay, so for the amplitude omega naught, so this is omega naught, 1 omega naught, the amplitude is A. 2 omega naught, so this is 2 omega naught. Okay, the 2 omega naught, the amplitude is B, and 3 omega naught, the amplitude is given as C. Alright. Next, how about the phase? For first omega naught, okay, for first omega naught, we don't have any phase here, right? Tak ada tambah theta. There's no plus theta here. So it is 0 lah. And for the 2 omega naught, we have positive pi. So meaning that we have positive pi here. And for 3 omega naught, okay, for 3 omega naught, the phase is become negative pi over 2. So it is, since that it is negative, so it is pointed downward. Okay, and the value is negative pi over 2. Alright. Okay, let's say if you have been given another conditions where the condition is the omega is same. Okay, we have a same omega, but for that same omega, we have both cosine and sine. Okay, so as I mentioned earlier, we don't want any sine in that equation. So we need to change everything that is sine to become cosine. Alright, and anything that is positive to become, anything that is negative to become positive. So in this case, we have cosine and sine, but both of this, the angular frequency. The frequency is same, omega n, omega n. So our objective to get as such, to become it as a cosine. And how to do that? So this is the method or the step that you need to do in order to change the form to become cosine. So to get the value of the amplitude, you need to sum, sum squared of both coefficient. So this is the coefficient for cosine and this is the coefficient for sine. So you squared, both of this coefficient, and then you plus. Next, the summation of that you need to square root of it. So that will become the amplitude. The amplitude. And how about the phase? How about the phase? So to get the phase, we need to use tangent inverse, in a bracket. Don't forget the negative here. So it's going to be Bn. So what is Bn? Bn is the coefficient for function coefficient for sine, and An is function coefficient for cosine. Alright, so to draw that, so once we got this equation, then only we can draw. So to draw, at omega n, so the frequency will not change, the frequency will remain the same. So the frequency is omega n, so at omega n the amplitude is become An based on the calculation earlier, and the phase is become theta n based on the equation earlier. Alright, so to test your understanding on that, let's look at this example. So sketch the magnitude and the phase spectrum of a signal which is given in a form of trigonometric Fourier series. So we have the equation here. So first of all, we need to check the component given. Don't forget. We need to check. We need to check the component given. Make sure everything is in a cosine form and everything in a positive equation. So in this case, we have how many? We have sine here, we have cosine here, and if we want to change, we see that the value of the frequency is given, both of it in omega naught. So therefore, we need to apply the method, the previous method just now. Next, we need to change this negative to become positive. Alright, so there are two things that we need to do. First, we need to come up sine and cosine that has this same frequency to become one equation of cosine. Next, to change this negative to become positive. So this is our objective. Alright, so what are the equation just now based on the step? First, we need to find the amplitude. So the amplitude is the coefficients of cosine plus the coefficient of sine, squared of it. And then we need to make it as a square root. So 2 squared plus 1 squared is equals to square root of 5. Next, how about the phase? So to find the phase, we need to have tangent negative, and don't forget there is a negative inside the bracket. Sine divided by cosine. So sine, the coefficient is 1 here. 1 and divide by 2. So we get the phase is negative 26.56. Next, don't forget, we need to change the negative behind here to become positive. So from negative to change into positive, negative cosine to become cosine. We need, to become cosine, we need to add pi, right? Theta plus pi. So we need to add pi behind here. So then you will get your final equation will become as such. So based on this equation, then only we can draw the magnitude and the phase spectrum. So by drawing, so 1 here, meaning that this is at 0. The value of omega here is 0. Omega naught here is equals to 0. So that's why it is 0 here. So 0, the amplitude is 1. And when the value of omega naught here become 1, at 1 omega naught, the value is, the amplitude is square root of 5, which is equivalent to 2.24, and at angular frequency of 2 omega naught, the amplitude is 2. Okay, amplitude or magnitude is the same. Okay, amplitude or magnitude. Okay, next, this is for the for the phase spectrum. So for the phase spectrum at 0 omega naught, we don't have any value of phase, so it is 0. And at omega naught, 1 omega naught, the value of the phase is negative 26.56 theta. 26.56 degree. So it is equivalent to 0.15 pi. So since that it is negative, so therefore it is pointed downward. Okay, at 2 omega naught, the value of the phase is 5 pi over 4, so it is equivalent to 1.25 pi. Since that it is positive, so it is pointed upward, right? Okay, we also can represent the equation by phasor representation. Okay, we also can we can also represent the equation given by phasor representation, okay, as shown as such. Alright, so this is the phasor representation. So let's say we have an equation here, a naught cos omega t plus theta naught. So how to draw the phase? So x will become your, we have a real x-axis and imaginary axis. Okay, so let's say that your phase, okay, phase value is positive. For example, in this case, yeah, we have positive theta. So since that it is positive, so when it is positive, the projection is in anti-clockwise directions. So meaning that at the real, from the real axis, we need to make it as anti-clockwise, so it will become in this direction. So it depends on what are the value of the theta here. Okay, let's say your theta is 30 degrees or 20 degrees, so it depends the angle here. Alright, so the angle here is depending on what are the value of the theta. So the direction, either it is anti-clockwise or clockwise, is dependent on the value of positive or negative. Alright, so A naught will gonna be the amplitude. So the length of this, is depending on the value of the amplitude. Alright, okay, so let's say we have another equation which is omega naught t minus theta naught. Okay, so in this case, let me use different color of pen. So in this case, since that it is negative theta naught, so you need to make it is clockwise direction. Okay, clockwise direction, and the value of this angle is depending on the value of theta. Okay, and the amplitude will be value of here. Okay, all right. Next, so just now I have explained about the trigonometric function. So we also have the complex exponential representation. So for complex exponential representation, okay, so it is used to analyze a signal, same as trigonometric. It just in another form. Okay, so just now this is our form for trigonometric function. But for complex exponential, we're going to have the exponential equation by using the Euler's theorem. So just now, since that our equation is in a cos equation, so in a complex representation, these will gonna be our equations. Okay, for example, this is the equation in a trigonometric function. So to change into the complex equation, it will become as such. So we can see here our amplitude. Okay, our amplitude in a complex form, it will be divided by 2. Why is it is divided by 2? Because based on this equation, okay, based on this equation, we have exponential j omega t plus theta naught plus exponential negative j omega t plus theta naught divided by 2. So this divided by 2, we can bring it in front, where we can divide the amplitude into 2. Okay, so theta here, so value of the theta here is depending on the value of in a general equation. Okay, it is the same value. Alright, so basically this equation is given or is used for a trigonometric equation, whereas the down equation, okay, is used in a complex exponential. So if you look at this equation given, okay, in an exponential here, we can see we have one side of positive, we have another side of negative exponential, right? So that's why in exponential complex exponential form, we have double-sided graph, okay, because of the one side of positive exponential and another negative side of negative exponential. All right, so we still have two graph, which is one is amplitude or magnitude and another one is a phase graph. Okay, so the quantity of the graph spectrum is same with the trigonometric, which we have amplitude graph and phase graph. So same goes with the complex exponential, we have amplitude graph and the phase graph. However, the only difference is for the trigonometric, we only have a single-sided, but for the exponential, we have double-sided. Right? So if we look here, the amplitude for exponential complex form, okay, the amplitude become V0 over 2. So we have one positive. Why it is positive? Because at this side, okay, at this side we have positive omega naught, right? Oh, sorry, in this here is omega, positive omega. So at positive omega, the value of the amplitude is V0 over 2, okay, V0 over 2. But we also have negative omega, right? At here, we have negative omega. So at negative omega, we still have the value of amplitude V0 over 2, okay? Because we have a brackets here. Maksudnya, kita kembangkan. You need to expand the bracket. So one amplitude is for positive omega. Another amplitude is for negative omega, right? Okay, next, for the phase. Okay, for the same goes for the phase. So we have positive phase. Okay, for this positive phase, the value of the angle is positive theta, right? Positive theta. But for negative omega, okay, negative omega, the value of the phase is become negative. Although it is positive, we have negative outside here. So when we expand the equation, it will become j omega t plus minus j theta. So we can ignore the j is because of the imaginary, we just take the value of theta. So since that it is negative, so it's going to be pointed downward. Alright? So phasor representation also can apply for the complex exponential. Alright? So we have, for the complex exponential, we have for example, this is for the polar representation or time domain, or also known as trigonometry. So we in a phasor form, A will become the amplitude. Okay, the length of this angle will become the amplitude, and the direction, either it is positive or negative, is depending on the value of the theta. Either it is positive or negative. If it is positive, it is anti-clockwise, and if it is negative, it's gonna be clockwise direction, right? So for complex exponential, okay, since that we have both, one it is positive and one in a negative, so we're gonna have double direction here. One we're gonna be clockwise direction, anti-clockwise direction, and another one we're gonna be clockwise direction. Okay, where the value of the amplitude is divided by 2. Okay, so in this case, this is A0. It's supposed to be A0 because the amplitude is A0. Can you make corrections in your slides? Alright, so this is A0 over 2 and this is A0 over 2. One will become positive, okay, which is anti-clockwise direction, and another one is negative theta, right? Clockwise direction, okay? So So in summary, we have time domain or trigonometry versus the exponential form. Okay, one is in this form, so in this form is known as a trigonometry or time domain form, and if it is in this form, when you see exponential, this is actually an exponential form. So what are the different? The different is the pattern of the graph. Okay, one we're going to be single-sided graph, another one we're going to be double-sided graph, but the content, the numbers of the graph, we still need to have amplitude spectrum and phase spectrum. Okay, now let's look at this example here. So in this question, they ask you to represent the signal xt. So this is the signal xt in the form of complex exponential Fourier series. So it's given to you in trigonometric function, right? Trigonometric function. So you need to change, or you need to convert from the trigo to become complex exponential Fourier series. So first of all, and then you need to sketch, right? And then you need to sketch. So first of all, you need to observe the equation first. If the equation is in a normal equations, okay, normal equations for trigonometry. So as mentioned, it must be in a sign, and all must be positive. So in this case, we have one sign here. So so we need to convert this sign to become cosine. Next, if any frequency sharing, you need to look if there is any frequency sharing. So we need to look at the frequency. This is 2 pi over 3, whereas this is 5 pi over 3. So obviously there is no frequency sharing. So we just need to rewrite the equation. So when we rewrite the equation, it will become cos 2 pi over 3 remain the same. However, for this sign to convert into cos, we need to add the negative pi over 2. So from here, we need to change into the exponential form. So exponential form, we're going to look as such, since that it is a cosine, so we need to use a cosine here. So since that there's no phase, so it will become only the frequency here. And here, since that there is a phase difference, so here it is. And from here, okay, from here we can draw the graph. So, okay, we can see at 0, so this is at 0 of angular frequency, yeah? The amplitude is 2, and the amplitude for positive 2 pi over 3, the amplitude is 0.5, and for negative 2 pi over 3, the amplitude is still 0.5, yeah? Next, for amplitude 5 pi over 3, the amplitude is 2, and for another negative 5 pi over 3, the amplitude is still the 2. So this is for amplitude spectrum. Next, we need to draw for the phase spectrum. So for the phase spectrum, at 2, there's no phase. Okay, it is 0. Okay, you can just leave it as 0. So same goes with 2 pi over 3. There's no phase involved here. Okay, however, there's a phase involved, which is negative pi over 2 at positive 5 pi over 3 angular frequency. So since that it is negative, so it is pointed downward. And next, at negative 5 pi over 3, the value of the angular frequency, so it is negative, so it will become positive pi over 2, right? So it is pointed upward, yeah? So here is the complex form that I have included for you guys, for you to refer, which later on, this might be beneficial for you guys in order to solve the Fourier series. So I hope you can use this, yeah? And thank you so much. See you on the next class, right?